All right. Hajimemashite, dozo yoroshiku. My name is Rich Collins, Director of Product Marketing for ARC Processors at Synopsys. And as I was introduced today, I will talk about our new products that are RISC-V based that we call ARC-V. I'll try to speak slowly, so hopefully everyone can understand, and hopefully we'll have time for any questions. So when we were looking at whether or not it made sense for us to move into building RISC-V processors, we started to look at the industry as a whole. As many of you may know, the ARC processor portfolio has existed for many decades, and we've been selling processors at Synopsys as part of that ARC portfolio for a long time, maybe 15 years or so now. And so when we looked across many industries, we saw some common threads, things like smart everything. So it is pretty much covering almost any industry, any application segment, software advances, as well as trends in semiconductor technology are driving a lot of these applications as well as machine learning. So AI and machine learning, those are pretty much across any industry, whether it's automotive, whether it's healthcare, whether it's data center. It touches on almost every single application that there is a semiconductor IP. And so if you look at these transformations that we're seeing across all of these industries, it's both the semiconductor advances in technology as well as IP advances, as well as the software. They are at the center of these major transitions across these industries. And software drives this differentiation, especially when we look at things like RISC-V, where the ISA is being standardized, and there are ways that we'll talk about to customize and extend the hardware aspects of it, but largely the differentiation is being driven by software. And to that end, both the software side as well as the SoC development side are looking toward open source solutions for both increased ability to collaborate across industries, across partnerships, ecosystem, as well as providing flexibility that they can build into their solutions. So as I'm sure many of you know that have been following RISC-V, as I mentioned, we've been following RISC-V for a number of years before we decided to eventually extend our portfolio and build RISC-V products. But especially over the last 1 or 2 years, the acceleration of activity around RISC-V has been exponential. So you look at things that have happened just in the last 12 months are very significant. Things like the launch of RISE, providing a software platform that's standardizing on RISC-V solutions across multiple industries. The RISC-V summits themselves are expanding across the world, obviously, because we're here. You see, it's not just in, for instance, North America. Europe had its first RISC-V summit this past summer. And then you see lots of activity with different companies. So for instance, there was a joint venture created this summer that now has basically appointed a board and has a name, and this joint venture is mostly focused on automotive, at least at first, with some of the major semiconductor players like Infineon, NXP, Bosch, Qualcomm, all coming together to standardize on RISC-V for automotive and eventually extend that to IoT and other application spaces as well. Qualcomm themselves have been a major proponent of RISC-V and have been very public about their support of RISC-V. And so, for instance, they basically ported their wearable platform Wear OS to RISC-V over the last couple of months. And then, of course, at the end of the year at the RISC-V Summit in California, we officially announced our portfolio that we call ARC-V, and I'll talk a little bit more about that. So in general, I think we are definitely seeing a strong trend in the adoption of RISC-V. There's over 4,000 members now, as I'm sure you're well aware. Over 100 chip companies that have been publicly acknowledging work on RISC-V based SoCs. Dozens of software companies as well, and many different industries. And of course, you can look at or read different analysts' assessment of the growth that RISC-V will take on. In particular, we looked at one company called the SHT Group that predicts that the annual growth rate for SoCs that are being developed based on RISC-V is expected to grow 40% basically each year. So you can see lots of activity and lots of different new designs every year that will be based on RISC-V processors. And in particular, that I think are very interesting to us as an ARC processor portfolio are things like automotive and IoT. And so you can see that, especially in automotive, there is a prediction that the automotive AI-based or AI-enhanced SoCs around automotive, that market will reach almost $1 billion in just a few short years. Similarly, on the IoT side, the expectation is that 30% of all IoT devices will basically support RISC-V processors in about 5 years. So you can see very rapid growth in many industries. These are just two examples of industries where we are already seeing very rapid adoption of RISC-V in these types of markets. One thing that we like to emphasize, because there's always a question that we get asked, if you're standardizing on a common ISA between different vendors, how do you differentiate? How is the Synopsys offering for RISC-V processors any different than other companies that are offering RISC-V? And really, it boils down to implementation. So a common ISA makes a lot of sense. It allows a broad ecosystem. It allows standardization of tools, middleware, other software products. But that's just one part of the story. So when you want to build a robust processor product, there's so many other things that you have to look at with respect to the ISA. There's the microarchitecture. What things are you doing to minimize power and area? The RTL design and verification. Verification is a huge area. You heard Larry talk earlier today from Paris, how verification is a very important part of being able to develop robust processor architectures and SoCs based on those processors. And this is critical across any application, but it's very critical when you look at things like automotive. We're having a very robust safety critical type of processor product is inherent in making sure that you build a safe product for the automotive or other safety, industrial safety, and things like that. So that's one of the areas that we feel Synopsys brings a very strong portfolio of tools and resources to complement the processors that we're offering in the market, such that we feel that our end customers will be given a much higher quality product that they can put into their SoCs and believe that they will have a very few respins of silicon, as well as have robust fault-tolerant types of SoCs. So what did we announce when we announced our new portfolio? So we didn't just want to announce one core or one CPU and then sort of make it look a little bit like it was sort of experimental. We decided that if we were going to enter into the RISC-V market, that we wanted to make sure we were doing that with a whole portfolio of products. And those products, at least our initial announcement, is come in 3 different families. On the left side, we have the RMX series. The RMX series are deeply embedded and embedded processor portfolio that are 3 and 5 stage pipeline cores. These are meant to be used in applications that need very small area, very low power, things like IoT devices. And I'll talk a little bit more about some of the applications that each of these core families are targeting. But again, very much a small area, small power. One thing that we had done on our previous architectures, the ARC Classic that we call it, or traditional ARC ISA, is we have a set of processors that combine RISC-based processing it along with DSP. So in many of the IoT applications that we target, when you're looking at things like face detection or gesture recognition or music playback, those types of functions that you typically see in those devices, that requires more signal processing. And at least to date, there hasn't been a signal processing standard ratified as part of RISC-V. I know there's some discussion about that and things being evaluated, but there's no basically ratified consistent DSP architecture at the moment. And so we've decided for these processors to take a lot of the advances that we made in the DSP ISA that we survived for our previous architecture and combine that with the RISC-V cores in these small little RMX devices. As you go to the middle column there, is a family that we call RHX. This is a family of real-time processors, 10-stage pipeline, dual issue, 32-bit processors. These are really meant to target sort of that mid-range of performance, but also where real-time, latency, predictable latency is required. And we see this a lot in the automotive space. This family can scale, so we wanted to build a product portfolio that can scale, and so this family can scale from a single core up to 16 cores. And you can see the part down there at the bottom of the block diagram. One of the things that we brought along as well from our previous architecture was this concept that we call the cluster network. And so that cluster network manages a lot of the communication and control across the larger scalable core. So for instance, the coherency, cache coherency among all the different CPUs within the processor. It manages quality of service. So if you want to be able to dial priority for data going to a certain subset of the cores versus other subset of the cores, that's controlled there. We also have the interfaces to the SoC, so all the outside interfaces to the NOC, to other system level resources, as well as a shared memory architecture, a shared cache, in this case an L2, that can be both an L2 and shared cluster memory or scratchpad memory, and you can program that memory to be whatever size you need. So that's the real-time cores. The other aspect that we've added within this family that's new for the ARC portfolio is hardware virtualization. So especially in this type of application, it's needed to have the ability to separate the cores within the cluster and have isolation of applications that run on those, so you can create multiple virtual workloads across the multi-core platform and have it all managed by a hypervisor. We see this especially in the migration to what's being called the software-defined vehicle in automotive. If you've followed automotive, if you're involved in the automotive industry, it's very, very important to keep isolation between safety-critical applications and non-safety critical applications. And as you run these applications all on a single multi-core processor, that's a challenge. And so by having hardware virtualization, it allows you to do that. You can run, for instance, a virtual workload that's running a non-safety application on Linux on a subset of these cores. And then right next to it, you can run a safety-critical application that's running, say, on an AUTOSAR RTOS, and they're sharing the multi-core architecture, and that's being handled by that hypervisor that will separate and isolate those workloads across the processor. And then on the far right side is the family that we call the RPX series. The RPX series are 64-bit processors. Some of the architecture and microarchitecture that you see in the middle column is shared on the RPX family. So for instance, the cluster network that I just talked about A lot of that is very similar. We've spent 4 or 5 years basically developing that and verifying that. And so we're reusing a lot of the microarchitecture for the cluster network between the RHX and the RPX series. But there are some other differences, though, between those. So for instance, this is typically where you would expect you would run, for instance, Linux distro, Ubuntu or Debian Linux on these types of applications. And so the memory hierarchy is more of a traditional cache hierarchy where you see separate IND L1 caches. We have a private L2 cache, a unified L2 per core. And then at the cluster level or the multi-core processor level, we have an L3. And that L3, again, can be shared between a traditional L3 and the shared cluster memory that I talked about with the RHX family. The other difference in this family, aside from being 64-bit, is we do support AMBA CHI. So for these types of applications, we do anticipate that you may see more than 16 cores required. So the single cluster can scale from 1 to 16. But for instance, if you needed 32 or 48 cores in your SoC, you still want to be able to maintain coherency across those multiple clusters. And the AMBA CHI interface allows that. And so we will support that so you can build multiple clusters of this RPX family into your larger SoC. Across the board, as we've done with our existing portfolio, functional safety is near and dear to us. We have a certified quality management system that is certified by third-party vendors for developing our IP. And then we also have what we call FS or FUSA versions of our products that have hardware mechanisms built in to support ISO 26262 hardware, random hardware requirements or fault detection requirements. And so we have special versions of the processors that support FUSA as well. So looking at the families, so these are the applications. Again, this is all synthesizable, retargetable IP that can more or less address any application that our customers would like to target it for. But there are certain applications that we typically focus on with our portfolio, and you can see them here: industrial, automotive, consumer, storage, as well as networking. And then within those types of applications, you can see the examples of the types of functions that you would address with the different families that we announced. So using the automotive example, the RMX family of embedded cores is going to target the types of functions that you would see for, low power in the car. For instance, sensors, keyless entry, anything that's body electronics type of focus. And then as you move up in terms of performance, that's where you would need something like a real-time processor to do things like infotainment or managing the gateway communication between all the pieces or the different aspects of the car, as well as safety management, overall safety management of the vehicle. And then as you move up to that concept of a software-defined vehicle where things are being centralized either zonally on each quadrant of the car or even a larger processor, say as a central processor in the car, then you obviously need a much higher performance processor for that. And that's where an RPX class of processor is going to be well suited there. So you can see that across the board, this is a very scalable family. And of course, these are all going to follow the RISC-V defined profiles. So for instance, the 32-bit ones will have several different flavors, all of them aligned to the profiles defined by the RISC-V standard. And then obviously the 64-bit will also align to the 64-bit apps processor profiles defined by the standard. So this gives a little bit detail of the processors that we've announced, but mostly I use this slide to focus on kind of where these processors came from, if you will. So the darker purple ovals on the left are our existing ARC native or ARC classic ISA-based processors, and then the lighter color purple ovals are the new ARC-V products that we've announced. And so you can see there kind of how we've derived and how we share a lot of the microarchitecture. So the products on the left have been in existence and they've been in mass production for a number of years. And one of the things that we've always focused on for our portfolio is making sure that we've built very PPA efficient products. So everything that we do is focused on making sure that it is efficient from a power and area perspective as possible. And so we bring a lot of that microarchitecture to the ARC-V cores. So our ARC-EM family is largely the basis of development for the RMX family. And you can see there we have several flavors of cores for RMX, where we have the ones with just RISC plus DSP, and then the FS ones are the ones that have special functional safety aspects built in. And then, as I said, we have 3- and 5-stage pipelines, so we have higher performance version of that. The RHX family is largely derived from a microarchitecture perspective from our HS5X family. Again, that cluster network that I talked about, where we have all of that logic that controls all of the functionality of the multi-core cluster, we're reusing that logic. So that logic's already been developed, it's already been verified, and that's the basis for the RHX family. And again, we have the RISC only, and then we have the scalar and vector version. So if you do need vector support in your product, then we will have vector-based support as well, following the RVB standard within the RISC-V standard itself. And then the RPX family at the top right, that is leveraging a lot of the microarchitecture from our HS6X family, our 64-bit HS products. Again, we want to leverage a lot of the work that we've done over the last 15 years in building very efficient, very low power, performance efficient processors, and reuse as much of that as we can. Obviously, there are plenty of changes that will have to come because we are, following a different ISA. The RISC-V ISA is not exactly the same as our ARC native ISA. So there are some microarchitecture changes that we have to support, especially on the front end, to change ISAs between the ARC classic ISA and the RISC-V ISA. But from the back end, if you will, a lot of the microarchitecture will be reused in leveraging the PPA gains that we've made over the last decades. Not to be forgotten, we also focused on our software tool suite. So in addition to partnerships that we've developed in the ecosystem with both our classic and now with our ARC-V portfolio for third-party support, we also have our own tool suite. The Metaware tool suite has been in existence for longer than even ARC has been in existence. So I think 35 years or something like that Metaware has been around. Metaware is a full tool suite that has the compiler, the debugger, instruction set simulator, cycle approximate simulator, the IDE, and several libraries are all part of the Metaware tool suite that exists for all of the existing ARC products. And we are extending that same exact tool suite to support the ARC-V portfolio as well. So we'll have a very efficient tool suite that customers can leverage. This will be very important, especially for customers that have already been using ARC and would like to then go to a RISC-V portfolio. They can have the exact same tool suite, the same IDE, the same look and feel that they have today, and use those tools for the ARC-V portfolio as well. So one of the other aspects that I think is important when you look at differentiation of the different RISC-V vendors and how they compare and contrast in terms of offering a quality product, one of the things that we wanted to make sure that we were doing is leveraging the bigger Synopsys, if you will, the greater Synopsys portfolio. So the EDA side of Synopsys has been doing work supporting RISC-V for a number of years. And we want to make sure that when we build our ARC-V portfolio, that we're taking advantage of all the things that Synopsys is doing because we have access to all of those tools. So for instance, optimizing quality of results and productivity, we're going to leverage the quick start kits that our virtualizer team has built to make it very easy to develop products around RISC-V. We want to leverage a lot of the architectural exploration type tools. So we have a set of tools we call ASIP, or application-specific processor development. So if you wanted to develop your own RISC-V processor, we've supported that for a number of years. And I think in years past, we've done presentations on our ASIP tools. But now we can leverage those ASIP tools in building and supporting sort of architectural exploration before customers need to make a commitment to buying IP, for instance, so they can do their own sort of customer architectural exploration and then leverage IP if they want to do that. We use those tools internally as well to do our own architectural exploration to play with the types of things that we want to build in future processors. We want to leverage things like virtualized VDKs, virtualized development kits. We want to leverage things like ZBoo to do hardware emulation. And so those are all aspects that we want to tap into and are tapping into to build out a very robust ARC-V portfolio. And then in addition, we're leveraging our ARC-V portfolio, but as well as the broader silicon or interface IP portfolio that Synopsys has to offer kind of one-stop shop for our customers that want to develop RISC-V-based SoCs. They have and can effectively purchase about all the IP that you might need for that SoC from Synopsys. Okay, so to wrap up, I think that we started to look at this a number of years ago. We do see a strong trend in SoC designers looking for open source solutions for collaboration as well as flexibility in developing their SoC solutions, as well as choice of vendors. With RISC-V, there are several different RISC-V vendors, so obviously that provides the SoC developer team a lot of choice. They have a lot of options in the industry that they can choose from, and so from that end, you have to basically provide some differentiation. You have to be able to provide a better version of the processor than, say, another vendor, but that's part of the competition part of it. And that's one of the reasons why we developed this ARC-V portfolio. We saw we have a very strong customer base with our existing IP, but we were increasingly getting questions, requests from customers and new customers on whether or not we would support RISC-V as an option. And so we see the growth in RISC-V. We're not abandoning our existing portfolio. We're not replacing our existing portfolio, but we're enhancing our existing portfolio by adding these new ARC-V cores so that our customers and our future customers will have a RISC-V option for developing SoCs with our IP. And so those options will then be available for CPUs, as well as complementing the existing portfolio that we have that I didn't talk about today, but some of what we call our specialty processors, our vector DSP families, our AI engines that we have in our portfolio. So these ARC-V, RISC-V processors complement that portfolio, giving our customers a very, very broad choice of processing options for building out whatever SoC, whatever type of SoC they are looking to build. Okay, so that was it. Any questions?
May I ask a question? So it's a very good presentation, but I'm still don't understand. What is the stage of development? It is a planning stage, under development, prototype, evaluation, blah, blah, blah. So
right. So you see in this slide, it kind of represents a little bit the timeline. Basically, we're developing over the next year and a half, all of these families. The embedded ones at the bottom will be the first available. So we will have those available starting in, say, about 3 months, 3 to 6 months. And then the RHX family will be available later in 2024. And then the RPX family will be available in the early part of 25. So basically, all of this will be is being developed now and will be available over the next year and a half.
Maybe just before development starts, right? So maybe just kind of.
No, we're in development now. We've been in development for about 6 months with these products. Yeah.
Any other questions? じゃあもう、じゃあ、sorry for one more question.
Okay.
According to my old knowledge, ARC was famous for very small controller for Wi-Fi chip. Your PC, my PC, everybody has very high, percentage uses ARC. But it's a very small embedded microcontroller. So, but your plan looks kind of huge leap for me.
Yeah, well,
So how do you
okay. Yeah, I mean, I
control
think,
the customer?
right. So I think your interpretation is partially true. We do have very small, low power cores. The ARC-EM family in particular that is used in some of the larger computer chips for controlling things like Wi-Fi and Bluetooth and whatnot. But we've had real-time controllers and we've had 64-bit processors in our portfolio for a number of years as well. So we do have what I call mid-range performance level processors in the portfolio today. So this is maybe some of the top end family will be a little bit higher performance, but not significantly higher performance. So it's not a huge leap for us to go from where we are to where we're going.
Yeah, sorry, my knowledge was not up to date.
No
Sorry,
problem.
so sorry. So 他にご質問ございますか？ではよろしいでしたね。はい。じゃあ、Thank you very much.
Thank you.